Tonight, we're going to explore one of the strangest things that happens in nature. An electron approaches a barrier. It does not have enough energy to cross it. Classical physics is absolute on this point. The electron must bounce back. There is no alternative. The barrier is forbidden. And yet, when physicists set up this exact experiment and measure what happens, they sometimes detect that electron on the other side. It didn't climb over the barrier. It didn't smash through it. It didn't secretly borrow extra energy from somewhere. But it's there. Sitting on the far side of something it should never have been able to pass through. This is quantum tunneling, and what actually happens during this process is far stranger, far more subtle, and far more important than most people ever realize. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already understand perfectly well. Barriers. You know what happens when you throw a tennis ball at a brick wall? The ball hits the surface and bounces back. It doesn't pass through. It doesn't slip between the bricks. It doesn't quietly appear on the other side. It's a solid surface, reverses direction, and comes back toward you. This feels so obvious it barely seems worth mentioning. Of course the ball bounces back. The wall is there. The ball can't get through it. End of story. Now imagine a slightly different situation. Instead of throwing a ball at a wall, you're rolling a marble toward a hill. The marble is moving along a flat table, and ahead of it you've placed a small ramp that rises upward to a peak and then slopes down on the other side. If you flick the marble hard enough, it climbs the ramp, crests the top, and rolls down the far side. You've given it enough energy to get over the hill, but if you flick the marble gently, something very predictable happens. The marble rolls partway up the slope, slows down, stops for an instant at whatever height its energy allowed it to reach, and then rolls back down toward you. Every single time. No exceptions. If the marble doesn't have enough energy to reach the top, it will never, under any circumstances, appear on the other side. This is one of the most fundamental ideas in all of physics. Energy is conserved. The marble possesses a certain amount of kinetic energy from its motion. As it climbs the hill, that kinetic energy converts into potential energy, the energy associated with height. If the hilltop requires more potential energy than the marble's kinetic energy can supply, the marble runs out of speed before it reaches the top. It has to come back. There's no other option. The energy simply doesn't balance any other way. This principle governs absolutely everything in the everyday world. It governs baseballs and boulders and bicycles. It governs cars and rockets and people. Every object you have ever seen, touched, or interacted with in your entire life obeys this rule without exception. If something doesn't have enough energy to cross a barrier, it stays on this side. Always. This is so deeply embedded in our experience that we don't even think about it. You don't walk into a wall and wonder whether you might pop out on the other side. You don't throw a rock at a cliff and expect it to appear in the valley behind it. These things don't happen. They can't happen. The physics is clear, and you've verified it every day of your life through sheer experience, even if you've never thought about the physics behind it. And for centuries, nobody had any reason to suspect there was a problem with this picture. Classical physics, the framework built by Isaac Newton in the late 1600s, and refined over the next 2 centuries by generations of brilliant mathematicians and experimenters, described the physical world with stunning accuracy. It could predict the arc of a cannonball, the swing of a pendulum, the orbit of a planet around its star, the motion of gears and pulleys and levers. Everything in the everyday world obeyed Newton's laws. Objects had definite positions. They moved along definite paths. When they hit barriers they couldn't cross, they bounced back. The universe was orderly. It was predictable. It made sense. In this classical picture, the world works like an incredibly precise machine. If you know exactly where every particle is and exactly how fast each one is moving, you can predict the entire future of the system. Nothing is left to chance. The future is completely determined by the present, and the present is completely determined by the past. There is no mystery. There is no ambiguity. There is only the relentless, clockwork unfolding of mechanical law. This was the picture of reality that physicists held for over 200 years. And it worked. It worked so well that by the late 1800s, some physicists believed the fundamental laws of the universe had been essentially figured out. All that remained were details, refinements, filling in the last decimal places. The British physicist Lord Kelvin reportedly said that the future of physics was to be found in the 6th decimal place, implying that the big discoveries had already been made. He was spectacularly wrong. Because even as Kelvin was expressing this confidence, cracks were already appearing in the classical foundation. And one of the earliest and most stubborn cracks involved something as ordinary as a hot piece of metal. When you heat an object, it glows. A piece of iron heated in a forge first glows a dull red, then orange, then yellow, then white as the temperature increases. Every object does this. The color and intensity of the glow depend on the temperature. Physicists in the late 1800s wanted to calculate exactly how much light a heated object should emit at each wavelength, from deep red through orange, through blue, and into the ultraviolet. Combining electromagnetic theory with thermodynamics should have produced a clean answer. It didn't. When physicists used the best classical theory available, the calculations worked well for long wavelengths, the red and infrared end of the spectrum. But as they pushed toward shorter wavelengths, toward the blue and ultraviolet, the formula predicted that the amount of energy radiated should increase without limit. It should climb higher and higher as the wavelength got shorter, eventually becoming infinite at the ultraviolet end. This was called the ultraviolet catastrophe, and it was deeply troubling. Obviously, a hot piece of metal does not radiate infinite energy. You can hold a piece of warm iron in your hand. The classical prediction was not slightly wrong. It was absurd. It was nonsensical, and no amount of clever mathematical adjustment within the classical framework could fix it. In 1900, a German physicist named Max Planck found a solution. But it required a radical assumption that Planck himself was deeply uncomfortable with. He proposed that the atoms in a heated object could only emit or absorb energy in discrete packets, tiny indivisible chunks that he called quanta. Energy, according to Planck's hypothesis, did not flow continuously like water from a tap. It came in specific minimum portions. Each quantum of energy was proportional to the frequency of the light being emitted. Higher frequency light, like ultraviolet, came in bigger packets. And at any given temperature, there simply wasn't enough thermal energy available to produce those bigger packets in large numbers. This naturally cut off the ultraviolet end of the spectrum, preventing the catastrophe. Planck's formula matched the experimental data perfectly, but Planck didn't fully understand why his own trick worked. He had introduced quantization as a mathematical device, almost a bookkeeping tool, to make the formula come out right. He hoped that someone would eventually find a way to derive his result using purely classical reasoning. Nobody ever did. Because energy really is quantized, Planck's reluctant assumption turned out to be a glimpse of a deeper reality. It was the first hairline fracture in the classical edifice, and through that fracture, everything that followed, the photon, the atomic model, the uncertainty principle, and ultimately quantum tunneling, would eventually pour in. But in 1897, 3 years before Planck's quantum hypothesis, another discovery was shaking the foundations of physics from a different direction. A British physicist named J.J. Thomson was working with sealed glass tubes that had metal plates at either end. When he applied a high voltage across the plates, mysterious rays traveled from the negative plate to the positive one. Scientists called them cathode rays, and nobody was sure what they were. Some physicists believed they were a form of light, some kind of electromagnetic wave. Others believed they were streams of tiny particles carrying electric charge. Thomson designed a series of careful experiments to settle the question. He used magnets and electric fields to bend the rays. If the rays were waves, they shouldn't be deflected by electric fields. But they were deflected. That meant they carried electric charge. By measuring exactly how much the rays bent under known electric and magnetic forces, Thomson calculated two critical properties. The rays carried negative electric charge, and the particles that made up those rays had an astonishingly small mass, far smaller than the lightest atom known at the time. Thomson realized he had found something entirely new, a particle smaller than an atom, a fundamental building block of matter that no one had known existed. He called it a corpuscle, though the name that stuck was electron. It was one of the most important discoveries in the history of science. For the first time, physicists had direct evidence that atoms were not the smallest things in nature. Atoms had internal structure, they contained even tinier components, and the electron was the first of those components to be identified. Today, we know a great deal about the electron. It carries a negative electric charge of about 1.6 times 10 to the negative 19 coulombs. Its mass is approximately 9.1 times 10 to the negative 31 kilograms. That number is so small it's almost meaningless in everyday terms. If you tried to write it out as a decimal, you would need to write a 0, then a decimal point, then 30 zeros, and only then would the first significant digit appear. The electron is extraordinarily, incomprehensibly light. A single grain of sand contains roughly 50 billion trillion electrons, and all of them together contribute a tiny fraction of the grain's total weight. The electron is also a fundamental particle. As far as physicists can tell, it has no internal parts. It's not made of smaller things glued together. There's no structure inside it, no gears, no subcomponents. It's elementary, one of the irreducible building blocks from which the physical world is constructed. Now, here's where you need to adjust how you think. Because when most people hear the word electron, they picture a tiny ball, a microscopic marble zipping through space along a clean, definite path. Maybe they picture it orbiting the nucleus of an atom like a miniature planet circling a miniature star. That image is everywhere. It's in textbooks. It's on science posters. It's in the logos of electronics companies. And it is deeply, fundamentally misleading. An electron is not a tiny ball. It does not look like a marble. It does not orbit the nucleus the way a planet orbits a star. Those images are rough sketches that help give a general impression of atomic structure, but they fall apart completely when you try to use them to understand what electrons actually do at the quantum level. And quantum tunneling is exactly the place where they fall apart most spectacularly. Here's why. In classical physics, the physics of everyday life, every object has a definite position at every moment. A tennis ball is at some specific point in space. You can photograph it. You can point at it. You can measure its location with a ruler. And at the same time, you can know its speed and the direction it's moving. Together, the position and velocity define the ball's state at that instant. And from that state, using Newton's laws, you can predict exactly where the ball will be at any future moment. The ball traces out a path through space, a continuous line from one position to the next. Physicists call this a trajectory. Classical objects have trajectories. They travel along definite, predictable paths. You can calculate those paths, and the calculations match reality perfectly. Electrons don't work this way. At the scale of atoms and subatomic particles, the rules change. An electron doesn't have a perfectly well-defined position and a perfectly well-defined velocity at the same time. This isn't because our measuring instruments are crude. It isn't because we haven't built precise enough detectors. It's because the electron genuinely does not possess both properties simultaneously with unlimited precision. This is a fundamental aspect of nature at the quantum scale. The universe itself does not assign a precise position and a precise momentum to an electron at the same instant. This is often associated with Werner Heisenberg's uncertainty principle, which he formulated in 1927. But the uncertainty principle isn't just a statement about measurement, it's a statement about reality. The electron literally does not have a perfectly sharp position and a perfectly sharp momentum at the same time. These quantities are complementary. The more precisely one is defined, the less precisely the other can be. Instead of a definite position and a definite trajectory, the electron is described by a quantum state. This quantum state is a mathematical description that contains everything nature allows you to know about the electron. And the predictions that emerge from this description are probabilistic. They don't tell you with certainty where the electron will be when you look for it. They tell you the probability of finding it in different locations. If you prepare 1,000 electrons in exactly the same quantum state and measure each one's position, you'll get a spread of results. Not because something went wrong, but because nature at this scale is inherently probabilistic. The individual outcome of a single measurement cannot be predicted with certainty, even with perfect knowledge of the electron's quantum state. You can only predict the statistical pattern that emerges over many measurements. This is radically different from how tennis balls behave. If you throw a tennis ball at a wall under identical conditions 10,000 times, it bounces back the same way every time. The outcome is determined. But if you send an electron toward a potential energy barrier under identical conditions 10,000 times, the results vary. Most of the time, the electron is reflected. But sometimes, a small number of times, it's detected on the other side of the barrier. And no amount of information about the electron's initial state lets you predict which individual electrons will tunnel through and which will bounce back. You can predict what fraction of them will tunnel, but not which specific ones. This distinction between the classical and quantum descriptions of reality is not a small technicality. It is the entire reason quantum tunneling exists. Now, let's talk about what physicists mean when they say potential energy barrier. Because this is one of the most commonly misunderstood ideas in quantum mechanics, and getting it wrong leads to a completely distorted picture of what tunneling actually is. When people hear the word barrier, they think of a wall. A physical wall made of brick or concrete or steel, something solid blocking the path. And then they imagine the electron somehow ghosting through that solid material, phasing through it like a science fiction character walking through a door. That is not what's happening. A potential energy barrier is not a physical wall. It is a region of space where the potential energy is higher than the particle's total energy. Let me explain that carefully. Think about the bicycle and hill analogy again. You're riding on flat ground with a certain speed. Ahead of you, the road rises steeply. The top of that hill represents a point of higher potential energy. To reach it, you'd need to convert your kinetic energy into potential energy. If you have enough kinetic energy, you make it over. If you don't, you roll back. The hill isn't blocking you because it's made of some impenetrable material. It's blocking you because climbing it costs energy you don't have. In the quantum world, a potential energy barrier works conceptually the same way. It's a region where an electron would need more energy than it possesses to enter. The barrier might be created by an electric field that pushes against the electron's charge. It might be a thin layer of electrically insulating material sandwiched between two conductors, like a sheet of non-conducting material only a few atoms thick, sitting between two pieces of metal. It might be the electrical repulsion between two positively charged atomic nuclei that are close to one another, each one's positive charge pushing the other away. In every case, the barrier is not a wall. It's an energy landscape. It's a region of space that costs more energy to occupy than the particle has available. Let me paint a specific picture to make this concrete. Imagine two thin sheets of metal placed almost touching, separated by an incredibly narrow gap. We're talking about a gap that might be only 1 or 2 nanometers wide, which is roughly 10 to 20 atoms across. An electron inside the first piece of metal has a certain amount of energy. To leave the surface of the metal, cross the gap, and enter the second piece of metal, the electron would need to overcome the energy barrier at the surface. This is sometimes called the work function. If the electron's energy is below this threshold, classical physics is unambiguous. The electron stays inside the first piece of metal. It cannot escape. It cannot cross the gap. It is stuck. And yet, in laboratories, electrons do cross that gap. A measurable electrical current flows between the two pieces of metal, even when no individual electron has enough energy to classically escape the surface. Real electrons. Real current. Reaching a destination that classical mechanics says is unreachable. Now think about what this means in terms of classical energy conservation. If an electron's kinetic energy is less than the barrier height, then entering the barrier region would require the electron to possess negative kinetic energy. Think about that carefully. Kinetic energy is 1/2 times the mass of the particle times the square of its velocity. Mass is always positive. The square of any real velocity is always positive. Therefore, kinetic energy can never be negative. It is physically impossible for a classical particle to have negative kinetic energy. This isn't a subtle point. It's a hard mathematical fact. And it's why the region inside the barrier is called the classically forbidden region. Classical physics doesn't just say the electron is unlikely to be there. It says the electron cannot be there. The mathematics forbids it absolutely. For any object that obeys classical mechanics, this prohibition holds without exception. A ball rolling towards a hill it doesn't have enough energy to climb will always roll back. A marble approaching a bump it can't surmount will always be reflected. A car driving towards a steep incline with insufficient power will always stop and slide backward. No exceptions, no loopholes, no creative workarounds. The energy doesn't add up any other way. This isn't a recommendation or a tendency. It is a hard, inviolable law of classical physics, as solid as anything in science. But electrons are not classical objects. They do not obey classical mechanics. They obey quantum mechanics. And quantum mechanics has a fundamentally different way of describing what happens when a particle encounters a barrier it doesn't have enough energy to cross. In the classical picture, when a ball hits a wall, the outcome is determined. The ball bounces back 100% of the time. In the quantum picture, when an electron encounters a potential energy barrier it classically cannot cross, the outcome is not determined in advance. Instead, quantum mechanics gives probabilities. There is some probability that the electron is reflected, and there is some probability, often very small but crucially not zero, that the electron is detected on the far side of the barrier. Not because it smashed through, not because it jumped over, not because it temporarily borrowed energy from some hidden reserve, but because the quantum description of the electron permits a non-zero chance of detection beyond the barrier, and experiments confirm that this chance is real. This is what happens in laboratories every single day. Physicists prepare many electrons in identical quantum states, send them toward the same barrier, and measure the outcomes. They find that most electrons are reflected, exactly as classical physics predicts, but a small, predictable fraction appear on the other side. The fraction changes depending on the barrier's properties, and it's always consistent with the predictions of quantum mechanics. It's repeatable, it's measurable, it's precise, and it absolutely cannot be explained by any version of classical physics. This is quantum tunneling. The phenomenon was first understood mathematically in 1928. A Ukrainian-born physicist named George Gamov was trying to explain something that had puzzled scientists for decades. Certain atomic nuclei spontaneously emit particles during radioactive decay. But when physicists calculate the energy of those emitted particles and compared it to the height of the energy barrier created by the nuclear force holding the nucleus together, the numbers didn't work. The particles didn't have enough energy to escape classically. They should have been permanently trapped inside the nucleus. And yet, they escaped. Regularly. Predictably. Gamov showed that quantum mechanics offered the answer. The particles were tunneling through the energy barrier. Their wavefunctions, a concept we'll explore in detail shortly, extended through the barrier rather than stopping abruptly at its edge. Around the same time, Ronald Gurney and Edward Condon independently reached the same conclusion. The classical picture of a particle trapped forever behind a barrier was incomplete. It worked perfectly for marbles and tennis balls, for everything in the everyday world. But at the scale of atoms and nuclei, a different set of rules governed reality. Rules that allowed particles to do something that seemed, from the classical perspective, flatly impossible. And this is not some rare, exotic curiosity confined to obscure experiments in specialized laboratories. Quantum tunneling is happening right now. It's happening in the device you're using to listen to this. It's happening in the nuclear reactions powering every star in the sky, including our sun. It's happening in the biological molecules inside your body. It's one of the most widespread and consequential phenomena in all of physics, operating silently at scales too small for the naked eye to detect, but producing effects that shape the entire visible universe. So the real question isn't whether tunneling happens. The evidence is overwhelming and has been for nearly a century. The real question is how. How does the quantum description of an electron permit something that classical physics absolutely forbids? The answer doesn't involve the electron cheating. It doesn't involve smuggling in extra energy or finding a secret passageway. The answer lies in the nature of the quantum description itself, in a mathematical object that replaces the classical notion of a trajectory, an object that doesn't stop where a classical particle would, that extends into regions where classical physics says nothing can exist, and that, under the right conditions, reaches through a barrier to create a real, measurable probability on the other side. That object is called the wave function, and understanding what it does inside a forbidden barrier is the key to understanding everything that comes next. A moment ago, I used a word you've probably heard before but may never have had properly explained. The wave function. This is the single most important concept in quantum mechanics, and understanding it is the key to understanding how tunneling works. So let's take the time to build it carefully. In classical physics, you describe a particle by saying where it is and how fast it's moving. That's the complete description. Position and velocity. From those two pieces of information, Newton's laws let you calculate every future instant of the particle's existence. You know its trajectory. You know where it was, where it is, and where it will be. Quantum mechanics throws this away. Not because physicists wanted to make things complicated, but because nature demanded it. When you work with electrons and other quantum particles, the classical description simply doesn't match what experiments reveal. You cannot simultaneously specify an electron's exact position and exact momentum with unlimited precision. And the electron does not follow a single definite path through space. Instead, quantum mechanics replaces the classical trajectory with something called the quantum state. And the mathematical representation of that quantum state is the wave function. The wave function is a mathematical function that assigns a complex number, a number with both a real and an imaginary part, to every point in space at every moment in time. The equation that governs how this function changes over time was written down in 1926 by the Austrian physicist Erwin Schrödinger. His equation, the Schrödinger equation, is to quantum mechanics what Newton's second law is to classical mechanics. It tells you how the wave function evolves. Given the wave function at one moment, the Schrödinger equation lets you calculate it at any future moment, provided you know the forces and energy landscape the particle is moving through. But here's where you have to be very careful, because the wave function is not what most people think it is. When people first hear about the wave function, they often imagine a kind of cloud, a smeared out blob of electron material spread across space, thicker in some places, thinner in others. They picture the electron as literally being spread out, occupying many locations at once like a fog filling a room. This image is wrong, and if you carry it in your head, you'll never understand tunneling correctly. The wave function is not a cloud of electron substance. The electron is not physically smeared across space like butter on bread. The wave function is a mathematical tool for calculating probabilities. It encodes what outcomes are possible when you make a measurement, and how likely each outcome is. It doesn't tell you where the electron actually is before you measure it. It tells you where you might find it if you look. The rule for extracting probabilities from the wave function was established by the German physicist Max Born in 1926. Born's rule says the following: Take the value of the wave function at some point in space. That value is a complex number. Now, take the absolute square of that complex number, meaning multiply it by its own complex conjugate. The result is a real positive number. That number gives you the probability density at that point. In plain language, it tells you the likelihood of detecting the electron in a tiny region around that location when you actually perform a measurement. Where the wave function's absolute square is large, there's a high probability of finding the electron. Where the absolute square is small, there's a low probability. Where the wave function is 0, there is 0 chance of finding the electron there. The electron isn't literally occupying all the places where the wave function is non-zero. It's just that if you measure, you could potentially find it at any of those places, with the odds given by the absolute square. This distinction matters enormously for tunneling. The wave function is not a physical wave of electron stuff rolling through space. It's a probability amplitude, a mathematical encoding of quantum possibility. When we say the wave function extends into a forbidden region, we don't mean electron material is leaking into that region. We mean the probability amplitude is non-zero there. And if the probability amplitude is non-zero, then Born's rule tells us there is a non-zero probability that a measurement will detect the electron there. Now, let's watch what happens when this wave function meets a potential energy barrier. Imagine an electron traveling through free space, moving toward a barrier. In the region before the barrier, the wave function looks like a wave. It oscillates. The exact shape depends on the electron's energy and momentum, but the key feature is that it oscillates. This oscillating form corresponds to a particle that has kinetic energy. It's moving, it's going somewhere. Now the wave function reaches the edge of the barrier. Remember, this barrier is a region where the potential energy is higher than the electron's total energy. Classical physics says the electron cannot enter this region because doing so would require negative kinetic energy, which is impossible for a classical particle. But the Schrödinger equation does not care what classical physics says. When you solve the Schrödinger equation for a barrier region where the potential energy exceeds the electron's total energy, you don't get 0. The equation doesn't suddenly produce nothing. Instead, the wave function changes character. It stops oscillating. Instead of going up and down like a wave, it decays. It drops off exponentially. But before we follow that decay deeper into the barrier, something important happens right at the boundary. Something that most explanations skip over, but that is essential for understanding why tunneling is probabilistic. At the very edge of the barrier, the incoming wave function doesn't simply continue forward into the forbidden region. It splits. Part of the quantum state reflects. Part of it penetrates. You can actually see an analogy for this in everyday life if you know where to look. When light hits a pane of glass, most of it passes through, but some of it reflects back. You see this every time you notice your own reflection in a window. The glass isn't a mirror. Most of the light goes through, but a fraction bounces back. The light encounters a boundary between two different materials, air and glass, and at that boundary, something interesting happens. The wave partially reflects and partially transmits. Both things happen simultaneously. You get a weaker transmitted wave on the far side and a reflected wave coming back toward you. Something conceptually similar happens when an electron's wave function reaches the edge of a potential energy barrier. The wave function encounters a boundary where the energy landscape changes. And at that boundary, the Schrödinger equation produces two components: a reflected wave traveling back in the direction the electron came from, and a penetrating component that enters the barrier region. These aren't two separate electrons, but the quantum state now has two components, one corresponding to reflection and one corresponding to penetration. The relative sizes of these components determine the probabilities. If the reflected component is large and the penetrating component is small, the electron is very likely to be reflected and very unlikely to tunnel through. If the reflected component is smaller and the penetrating component is larger, the tunneling probability goes up. This splitting happens at the boundary itself, before the wave function even begins its exponential decay inside the barrier. The barrier doesn't just attenuate the wave that enters it, it also reflects a portion right at the entrance. The fraction that enters the barrier is already reduced compared to the original incoming wave, and then that reduced portion decays exponentially as it crosses the forbidden region. So the tunneling probability is shaped by two effects: the initial split at the boundary and the exponential decay across the barrier's width. Both matter. Now let's follow the penetrating component into the barrier. This is where exponential decay takes over. The wave function's amplitude decreases by a fixed fraction for every additional unit of distance into the barrier. If you go 1 nanometer into the barrier, the amplitude might drop to 1/3 of its value at the edge. Go another nanometer, and it drops to 1/3 of that remaining value, which is 1/9 of the original. Another nanometer, and it's 1/27th, then 1/81st, then 1/243rd. The decay is relentless and steep. Every step deeper into the barrier costs the wave function a fixed proportion of whatever amplitude it still has left. This exponential character is absolutely critical. It's what makes tunneling sensitive to barrier width, and it's what prevents you from tunneling through your bedroom wall. But here's the key. Exponential decay approaches zero. It gets smaller and smaller, vanishingly small over large distances. But for a barrier that is thin enough, the wave function does not quite reach zero before it emerges on the far side. If the barrier is narrow, just a few nanometers or even less, the exponentially decaying wave function still has a small, non-zero amplitude when it reaches the far edge of the barrier. And beyond the barrier, where the potential energy drops back down, the wave function starts oscillating again. It's a traveling wave once more, just with a much smaller amplitude than the original wave on the incoming side. That diminished wave beyond the barrier represents a real, measurable probability. If you place a detector on the far side of the barrier, there is a non-zero chance it will register the electron's arrival. The chance is small. For many barriers, it's very small, but it is not zero. And when you run the experiment many times with identically prepared electrons, you find that a predictable fraction of them do appear beyond the barrier, every single time. The fraction matches the prediction of quantum mechanics with exquisite precision. Let me be very clear about what detection looks like. When you actually measure an electron that has tunneled, you don't find half an electron on one side and half on the other. You don't find a ghostly, translucent electron inside the barrier. You find a whole electron, the full charge, the full mass, entirely on one side or entirely on the other. The wave function might extend across the barrier, but the measurement result doesn't reveal a smeared out entity. It reveals a definite particle at a definite location. What the wave function gives you is the probability of which side you'll find it on. In a single trial, you send one electron toward the barrier and measure it. You get one result. Either you detect it on the incoming side, reflected, or you detect it on the far side, transmitted. There is no in-between, no partial tunneling, no half measures, just one electron found at one place. Now imagine you are a physicist in a laboratory and you are actually running this experiment. You have an electron source on one side, a thin barrier in the middle, and a detector on the far side. You fire a single electron. Your detector clicks. You check the readout. The electron was reflected. It didn't make it through. You fire another one. Reflected again. Another. Reflected. Another. Reflected. Dozens of electrons, all bouncing back. This is what you expect. Classical physics says they should all bounce back. For a while, the experiment looks perfectly classical. Then, on the 63rd electron, something different happens. Your detector on the far side clicks. An electron has appeared beyond the barrier. You check your equipment. Nothing went wrong. There's no malfunction, no stray electrical signal, no noise in the system. A real electron, with the full expected charge, triggered the detector on the far side of a barrier it didn't have enough energy to cross. You record the result. You keep going. Over the following hours, the pattern repeats. Long stretches of reflections punctuated by occasional tunneling events, arriving unpredictably. Over the course of the afternoon, you fire 10,000 electrons at the barrier. You count how many were reflected, and how many appeared on the far side. The answer is 9,803 reflected, and 197 transmitted. Your theoretical prediction, based on the Schrödinger equation and the known properties of your barrier, was a tunneling probability of 2%. 2% of 10,000 is 200. You measured 197. The match is extraordinary. But here's what haunts you as you pack up the lab for the evening. You cannot say anything about which electrons tunneled and which didn't. Electron number 63 tunneled, and electron number 62 didn't, even though they were prepared identically. They had the same energy. They approached the same barrier. Everything about them was the same, as far as quantum mechanics allows you to specify, and yet one tunneled and the other didn't. There is nothing in the theory, nothing in any version of quantum mechanics that tells you why that specific electron was the one that made it through. The theory only gives you the overall fraction. The individual outcomes are genuinely, irreducibly random. This is not randomness born of ignorance. It's not that you're missing some hidden variable, some secret property of the electron that, if only you could measure it, would tell you in advance whether it will tunnel. Theoretical work by John Bell in the 1960s, followed by increasingly precise experiments over the following decades, has shown that no local hidden variable theory can reproduce the predictions of quantum mechanics. The randomness appears to be fundamental. Nature, at this level, does not determine individual outcomes in advance. It determines probabilities, and those probabilities are obeyed with stunning precision over large numbers of events. But run the experiment 1,000 times, 10,000 times, 1,000,000 times, always with identically prepared electrons approaching the identical barrier, and the pattern emerges, a definite statistical pattern. Suppose quantum mechanics predicts a tunneling probability of 1%. Then, out of 10,000 electrons sent toward the barrier, roughly 100 will be detected on the far side. Not exactly 100 every time, because probabilities produce statistical fluctuations, but the average will converge on 100 out of 10,000. The more trials you run, the more precisely the fraction matches the theoretical prediction. This is not magic. It's not randomness in the sense of chaos. It's structured randomness, predictable unpredictability. Each individual electron's fate is uncertain, but the collective behavior of many electrons is precisely determined by the wavefunction and the Schrödinger equation. Quantum mechanics doesn't tell you what happens in each case, it tells you what happens on average, and its averages are extraordinarily, almost unreasonably accurate. Now, I need to address something important because nearly every popular explanation of tunneling gets this wrong. You will often read, in books and articles and online posts, that the electron borrows energy from the uncertainty principle to get through the barrier. The idea is that Heisenberg's uncertainty principle allows brief fluctuations in energy. The electron supposedly borrows a little extra energy, uses it to climb over the barrier, and then pays it back before the universe notices. This explanation sounds elegant, it sounds clever, and it is wrong. The energy-time uncertainty relation in quantum mechanics does not work the same way as the position-momentum uncertainty relation. The position-momentum relation involves two measurable quantities, position and momentum, that have well-defined roles as quantum operators. The energy-time relation is subtler. Time in quantum mechanics is not an observable in the same sense that position and momentum are. It plays a different mathematical role. You cannot simply say that the electron borrows energy for a short time and pays it back. That's a classical story dressed in quantum clothing, and it doesn't match the actual mathematics. Here's what actually happens during ordinary tunneling, stated plainly. The total energy of the electron before it reaches the barrier, while it interacts with the barrier, and after it appears on the other side, is the same. Energy is conserved. The electron on the far side of the barrier has the same total energy it had before. It didn't gain energy to cross. It didn't borrow energy temporarily. It didn't lose energy in the process. The energy before and after is identical. The resolution isn't that energy conservation is violated temporarily. The resolution is that the classical reasoning was wrong. Classical mechanics says that being inside the barrier would require negative kinetic energy, which is impossible. And classical mechanics is right about classical objects. But the electron isn't a classical object. It doesn't possess a definite kinetic energy at each point inside the barrier in the way a classical particle would. The wave function extends into the barrier, but this doesn't mean a little ball is sitting inside with a well-defined negative kinetic energy. The concept of a definite kinetic energy at a definite position inside the barrier doesn't apply to a quantum particle in the same way it applies to a marble. The electron doesn't need to borrow energy, because the framework that said it needed extra energy in the first place was the classical framework, and the classical framework doesn't apply here. Quantum mechanics tells a consistent story in which energy is conserved throughout the entire process, without any borrowing, lending, or temporary violations. The tunneling happens not because energy rules are broken, but because quantum particles are not governed by the definite trajectories that classical energy arguments assume. This brings us to one of the most fascinating and genuinely unresolved questions in quantum physics. How long does tunneling take? If the electron appears on the far side of the barrier, how long was it inside? Did it spend time crossing the forbidden region? Did it cross instantaneously? Is the question even meaningful? You might think this would be straightforward. The barrier has a width. The electron starts on one side and ends up on the other. Surely you can just time how long the transit takes. But in quantum mechanics, Nothing involving measurements inside a process is ever that simple. The problem is that asking how long the electron spent inside the barrier assumes the electron was a definite thing at a definite place during the tunneling process. It assumes the electron entered the barrier at a specific moment, traveled through it along some path, and exited at a specific later moment. But the wave function picture doesn't support this. The electron isn't inside the barrier the way a car is inside a tunnel. The wave function extends across the entire barrier region simultaneously. There is no moment where a localized particle enters, no moment where it exits, and no clean trajectory in between. Physicists have defined several different quantities that can be called tunneling times. Each one captures a slightly different aspect of what happens during the tunneling process, and they can give different answers. One approach is to compare the time it takes for the peak of a wave packet to appear on the far side of the barrier with how long it would take to travel the same distance in free space. This is sometimes called the phase time or group delay. Experiments measuring this kind of delay have found something remarkable. In some cases, the delay associated with tunneling through a barrier is extremely short, shorter than the time it would take for the electron to travel the same distance through empty space. This has led to dramatic headlines about electrons tunneling faster than light, but those headlines are misleading. The phase time or group delay does not mean the electron physically traveled through the barrier at a speed exceeding the speed of light. The peak of the wave packet on the far side can appear quickly because it's constructed from the leading edge of the incoming wave function, the part that arrived earliest and was already partially extending through the barrier. It's a reshaping of the wave, not a physical object moving superluminally. No information is transmitted faster than light. No energy is transported faster than light. No signal that you could use to communicate arrives at the far side sooner than light would. The fundamental speed limit of the universe is not violated. Another approach involves measuring how long a quantum clock, something like the precession of a particle's spin in a magnetic field, ticks while the particle interacts with the barrier region. These measurements give a different answer. They suggest a very short but non-zero interaction time. The particle's spin responds to conditions inside the barrier for a brief, measurable duration. The honest answer to how long tunneling takes is that it depends on exactly what you mean by the question. There is no single, universally agreed upon tunneling time. Different definitions capture different physical aspects of the process, and the results don't always agree. Some definitions give times that are very short. Others give times that depend on barrier width. Some seem to suggest near instantaneous traversal. Others suggest a finite, measurable duration. What all physicists agree on is this: quantum tunneling does not allow you to send a message faster than light. It does not allow matter to travel faster than light. It does not violate relativity. It does not create a loophole in the cosmic speed limit. The subtleties of tunneling time are real and fascinating, but they do not break the foundational principles of physics. And this is worth emphasizing because popular science often makes tunneling sound like a violation of the rules. It's not. Tunneling is not the electron breaking the laws of physics. It is the laws of physics operating in a regime where classical intuitions fail. Everything about tunneling is consistent with quantum mechanics. Energy is conserved. Causality is preserved. The speed of light remains the absolute limit for information transfer. What changes is our picture of what a particle is and how it moves through the world. The electron isn't a tiny ball following a forbidden path through the barrier. It's a quantum entity described by a wave function, and that wave function extends through the barrier in a way that creates a measurable probability of detection on the far side. This is the heart of quantum tunneling. Not violation, but description. Not cheating, but a deeper understanding of what particles actually are and how they actually behave. The wave function doesn't stop at the edge of a forbidden barrier. It decays inside it, exponentially, losing amplitude with every fraction of a nanometer. But if the barrier is thin enough, a remnant survives. A small oscillating wave emerges on the far side. And that small wave carries a probability. A chance, sometimes tiny, sometimes substantial depending on the barrier, that the next electron you send will be the one that appears where classical physics says nothing could possibly be. The obvious next question, the question that makes tunneling not just a curiosity but a phenomenon of immense practical importance, is what controls that probability. What determines whether an electron has a 1 in 100 chance of tunneling, or a 1 in a trillion chance? What makes some barriers easy to tunnel through and others essentially impossible? And why don't the objects in your living room tunnel through the floor? The answers lie in 4 quantities that together govern every tunneling event in the universe. 4 things determine whether an electron will tunnel through a barrier. Just 4. And every tunneling event in the universe, from the interior of a star to the circuits inside your phone, is governed by the interplay of these 4 quantities. They are the width of the barrier, the height of the barrier relative to the electron's energy, the electron's own energy, and the mass of the particle attempting to tunnel. Let's take them one at a time, because each one tells us something crucial about why tunneling happens the way it does, and why it doesn't happen in situations where you might naively expect it. The first factor is barrier width. This is the single most important variable in determining tunneling probability, and the reason is the exponential decay we discussed earlier. Remember what happens to the wave function inside the classically forbidden region. It doesn't oscillate, it decays. Its amplitude shrinks by a fixed proportion for every additional unit of distance into the barrier. If the amplitude drops to 1/3 of its starting value over the first nanometer, it drops to 1/9 after 2 nanometers, 1/27 after 3, 1/81 after 4. Each additional nanometer of barrier width costs the same fractional reduction. This exponential behavior means that small changes in width produce enormous changes in tunneling probability. Doubling the barrier width doesn't halve the probability. It can reduce it by a factor of thousands or millions or more, depending on the other parameters. Tripling the width reduces it by an even more staggering factor. The relationship isn't linear, it's not even polynomial, it's exponential, and exponential functions are among the most aggressive curves in all of mathematics. Think about it this way. Suppose the tunneling probability through a barrier 1 nanometer wide is 1%. That means 1 out of every 100 electrons makes it through. Now double the barrier width to 2 nanometers. The probability might drop to something like 1 in 10,000. Triple it to 3 nanometers, and you might be looking at 1 in a million or less. The exact numbers depend on the other factors, but the pattern is always the same. Every additional increment of width devastates the tunneling probability because the wave function has to maintain its exponentially decaying amplitude across a longer and longer distance. This is why tunneling is a short-range phenomenon. It matters when barriers are nanometers wide, or fractions of a nanometer. It becomes negligible when barriers are micrometers wide. And it is laughably, preposterously, inconceivably unlikely when barriers are centimeters or meters wide. The difference between a nanometer and a centimeter is a factor of 10 million. That factor of 10 million sits in an exponent. The resulting probability is so small that writing it down requires more zeros after the decimal point than there are atoms in the observable universe. This alone explains why you don't fall through the floor. The barriers between atoms in a solid object are, from a quantum tunneling perspective, enormous. Not because they're physically thick, but because they're thick enough relative to the incredibly short distances over which tunneling operates. A barrier that is a few nanometers wide is already pushing the limits. The spaces between atoms in a solid, while tiny by everyday standards, are vast by tunneling standards. The second factor is barrier height. The height of the barrier is the difference between the potential energy at the top of the barrier and the total energy of the electron. A taller barrier, one where the potential energy significantly exceeds the electron's energy, causes the wave function to decay more steeply inside the barrier. Each nanometer of distance costs a larger fraction of the remaining amplitude. A shorter barrier, one where the potential energy only slightly exceeds the electron's energy, causes a gentler decay. The wave function still shrinks, but more slowly, so more amplitude survives to reach the far side. You can think of it this way. Imagine two hills, both the same width at the base. One is a gentle slope, the other is a steep cliff. If the wave function is decaying as it crosses these barriers, the gentle slope corresponds to a low barrier where the decay is gradual, and a steep cliff corresponds to a tall barrier where the decay is severe. Even if both barriers have the same width, the gentle one allows much more amplitude to survive. The probability of tunneling through a low, thin barrier can be millions of times higher than the probability of tunneling through a tall barrier of the same width. The third factor is the electron's own energy. This is closely related to barrier height, because what matters physically is not the absolute height of the barrier, or the absolute energy of the electron, but the difference between them. If the barrier height is 10 electron volts above the electron's energy, the decay inside the barrier is steep. But if the electron has slightly more energy, say the barrier is only 5 electron volts above the electron's energy, the decay is gentler. The wave function doesn't shrink as aggressively. More amplitude reaches the far side. The tunneling probability goes up. At one extreme, if the electron's energy exactly equals the barrier height, there is essentially no forbidden region. The electron can classically just barely make it over. In this limit, the tunneling probability approaches something close to certainty, depending on the exact shape of the barrier. At the other extreme, if the electron's energy is far below the barrier height, the decay inside the barrier is extremely steep, and the tunneling probability becomes vanishingly small even for thin barriers. So, the first three factors, width, height, and electron energy, all connect to the same underlying mechanism. They all affect how much the wave function decays inside the barrier. Anything that makes the decay gentler or the distance shorter increases the tunneling probability. Anything that makes the decay steeper or the distance longer decreases it. But the fourth factor is the one that truly explains why quantum tunneling belongs to the realm of electrons and atoms rather than baseballs and people. The fourth factor is mass. The rate at which the wave function decays inside the barrier depends on the mass of the particle. Heavier particles have wave functions that decay much more steeply than lighter ones, all else being equal. This relationship comes directly from the Schrödinger equation. The decay rate inside the barrier is proportional to the square root of the particle's mass multiplied by the difference between the barrier height and the particle's energy. The mass sits inside a square root, so you might think its influence would be modest. It is not. It is devastating. An electron has a mass of about 9.1 times 10 to the negative 31 kilograms. A proton, by comparison, is about 1,836 times heavier. Because the decay rate depends on the square root of the mass, a proton's wave function decays about 43 times faster inside the same barrier. That factor of 43 sits in an exponent. The tunneling probability for a proton through the same barrier that an electron crosses with reasonable ease can be billions upon billions of times smaller. And a proton is still extraordinarily light by everyday standards. Think about the mass of a grain of sand. A typical grain of sand has a mass of roughly 50 micrograms, which is about 50 times 10 to the negative 9 kilograms. That's approximately 10 to the 22nd power times the mass of an electron. When you put a number that large into the exponential decay formula, the tunneling probability becomes a number so absurdly small that there is no meaningful way to express it. It's not just unlikely in the way that a lottery win is unlikely. It's not unlikely in the way that being struck by lightning twice on the same day is unlikely. It's a probability with so many zeros after the decimal point that if you wrote one digit on every atom in the observable universe, you would run out of atoms long before you finish writing the number. This is why macroscopic objects don't tunnel through walls. It's not that quantum mechanics forbids it in principle. Technically, the equations assign a non-zero probability to a baseball passing through a concrete wall. The wave function of the baseball doesn't cut off sharply at the wall's surface. It decays, just like an electron's wave function would. But the mass of a baseball is so enormous compared to an electron that the decay rate is incomprehensibly steep, and the barrier width of a concrete wall is so vast compared to the nanometer scale barriers that electrons encounter. The combined effect makes the probability so small that it might as well be zero. Not approximately zero, not practically zero. So far below any meaningful threshold that the word zero is the only honest description. If every atom in the observable universe threw a baseball at a wall once every second, and they kept doing this for the entire current age of the universe, and then did it again for another universe age, and repeated this process a billion times, the probability that even a single baseball would tunnel through would still be effectively zero. The universe doesn't have enough time, enough baseballs, or enough walls to make macroscopic tunneling happen even once. This is the answer to the question that many people ask when they first learn about quantum tunneling. Can I walk through a wall? No. Not in any practical or meaningful sense. The physics doesn't strictly forbid it. But the probability is so unimaginably small that even calling it possible is misleading. It's like saying it's possible for all the air molecules in your room to spontaneously move to one corner and leave you in a vacuum. The laws of physics permit it, but it will never happen. Not in the lifetime of this universe. Not in the lifetime of 1 trillion universes. Mass is the great separator between the quantum world and the everyday world. It's the reason electrons and protons and alpha particles can tunnel through energy barriers, while sand grains and tennis balls and human beings cannot. The dividing line isn't sharp. There's no specific mass where tunneling suddenly switches off. It's a continuous decline in probability as mass increases. But the decline is so steep that by the time you reach even a modest molecule, let alone a macroscopic object, the tunneling probability through any reasonable barrier has already plummeted to numbers that defy comprehension. This helps clarify something about the physical meaning of the Planck constant, the fundamental constant of quantum mechanics, usually written as h or h bar. This constant sets the scale at which quantum effects become important. Its value is incredibly small by everyday standards, about 6.63 times 10 to the negative 34 joule seconds. This tiny value is the reason quantum effects like tunneling are invisible at macroscopic scales. If the Planck constant were much larger, quantum tunneling would be noticeable in everyday life. Objects would have a realistic chance of passing through barriers. The world would be bizarre and unpredictable in ways that would make macroscopic structure and stability essentially impossible. The fact that the Planck constant is so small confines noticeable quantum behavior to the scale of atoms and subatomic particles, where masses are tiny enough and distances are short enough for quantum effects to matter. Now, before we move on to the most elegant demonstration of tunneling ever built, let's put all four factors together in a single picture. Because individually, each factor makes sense. Width matters, height matters, energy matters, mass matters. But tunneling is governed by all four simultaneously, and seeing how they interact is what transforms this from a list of variables into a visceral understanding of when tunneling matters and when it doesn't. Imagine a concrete scenario. An electron is approaching a barrier that is 1 nanometer wide. The barrier height is 5 electron volts above the electron's energy. At these values, the tunneling probability works out to roughly a few percent. That's significant. You'd measure a real, detectable tunneling current. Now keep everything else the same and change just the width. Make the barrier half a nanometer wide instead of 1. The wave function now has to decay across only half the distance. The amplitude on the far side is much larger. The tunneling probability jumps dramatically, perhaps to 20 or 30%. Nearly a third of the electrons make it through. Tunneling has gone from an occasional event to a routine one. Now, go the other direction. Make the barrier 2 nanometers wide instead of 1. The wave function has to survive twice the original distance of exponential decay. The probability doesn't just halve, it collapses. Instead of a few percent, you might be down to a few thousandths of a percent. Out of 100,000 electrons, only a handful get through. The barrier is only twice as wide, but the probability has dropped by a factor of 1,000 or more. Reset the width back to 1 nanometer and now change the height. Keep the electron's energy the same but double the barrier height, so the potential energy is now 10 electron volts above the electron's energy instead of 5. The wave function decays more steeply with every step into the barrier. The probability drops sharply, perhaps by a factor of 100 or more. The same 1 nanometer barrier that a few percent of electrons could tunnel through at 5 electron volts above their energy now blocks all but a tiny fraction at 10 electron volts above. Reset the height and now raise the electron's energy instead. If the electron's energy is only 1 electron volt below the barrier rather than 5, the difference between them is small. The decay inside the barrier is gentle. The probability climbs. It might reach 10, 20, even 30% or more. The electron doesn't have quite enough energy to classically clear the barrier, but it's close. And that closeness translates directly into a higher chance of making it through. Finally, the most dramatic change of all. Reset everything to the original configuration, the 1 nanometer barrier, 5 electron volts above the electron's energy, a few percent tunneling probability. Now replace the electron with a proton. Keep everything else identical. Same barrier width, same barrier height, same energy deficit. The only thing that changes is the mass of the particle, from 9.1 times 10 to the negative 31 kilograms to 1.7 times 10 to the negative 27 kilograms. The proton is about 1,836 times heavier. And the tunneling probability doesn't just decrease, it effectively vanishes. The few percent chance the electron had becomes a probability so small it would take more digits to write down than there are particles in the solar system. This is what the 4 factors look like when they work together. Each one is a knob. Turning any single knob changes the probability. But the interactions between them are what produce the enormous range of tunneling behaviors we see in nature. From the substantial tunneling currents that flow in scanning tunneling microscopes, to the vanishingly rare events that allow alpha particles to escape nuclei over billions of years, to the effectively zero probability that a baseball will ever pass through a concrete wall. Now, let's see these 4 knobs in action in the most direct, most elegant demonstration physicists have ever devised. A device so sensitive that it can feel the shape of individual atoms. The scanning tunneling microscope. In 1981, 2 physicists working at the IBM research laboratory in Zurich, Switzerland, built something extraordinary. Their names were Gerd bin Ig and Heinrich Rohrer. What they constructed was deceptively simple in concept, but profoundly difficult in execution. They took an extremely sharp metallic needle, sharpened to such a fine point that the very tip ideally consisted of a single atom. They mounted this needle above a conducting surface with an incredibly small gap between the tip and the surface. Then they applied a small voltage between the tip and the surface and measured the resulting electrical current. Classical physics says there should be no current. The gap between the tip and the surface is an insulating vacuum. There's no conducting path for electrons to follow. It's like holding 2 wires close together but not touching them. No current should flow. The electrons in the tip don't have enough energy to jump across the gap. They're trapped behind a potential energy barrier created by the vacuum between the tip and the surface. But the gap bin Ig and Rohrer used was extraordinarily narrow. Just a few angstroms. An angstrom is 1/10,000,000th of a meter. It's roughly the diameter of a single atom. At this distance, the gap between the tip and the surface is only a few atoms wide. And at that scale, quantum tunneling becomes significant. Electrons from the tip can tunnel across the vacuum gap and reach the surface, or vice versa. A measurable current flows even though no classical current should be possible. This current is the tunneling current. Here's what makes this useful, and not just interesting. Remember that the tunneling probability depends exponentially on barrier width. The gap between the tip and the surface is the barrier. If you change that gap by even a tiny amount, even a fraction of an angstrom, the tunneling current changes dramatically. An increase in the gap of just 1 angstrom can reduce the current by roughly a factor of 10. This extraordinary sensitivity is what transforms a laboratory curiosity into one of the most powerful imaging tools ever created. Think about what a conducting surface looks like at the atomic scale. It's not flat. It's a landscape of individual atoms, each one sitting at a slightly different height, arranged in whatever crystal pattern defines that material. Some atoms protrude a tiny bit more than others. The surface is bumpy at the angstrom scale. When you scan the sharp tip across this surface, maintaining a constant height, the tunneling current fluctuates as the tip passes over individual atoms. Above an atom, the gap is slightly smaller and the current is higher. Between atoms, the gap is slightly larger and the current drops. By recording these current fluctuations as the tip sweeps back and forth across the surface, you can build a map of individual atoms. You're literally feeling the surface atom by atom, not with light, not with any form of imaging that involves bouncing photons off the surface, but with the quantum mechanical tunneling current that flows between the tip and each atom it passes over. In practice, most scanning tunneling microscopes operate in a slightly different mode. Instead of holding the tip at a constant height and measuring changes in current, they use a feedback loop. The current is kept constant and the height of the tip is adjusted automatically to maintain that constant current. When the tip passes over an atom and the current starts to increase, the feedback circuit pulls the tip slightly higher. When the tip moves between atoms and the current starts to drop, the circuit pushes the tip slightly lower. By tracking how much the tip's height changes as it scans across the surface, you build a topographic map of the atomic landscape beneath it. The result is an image, not a photograph in the traditional sense, but a data map that reveals the positions of individual atoms on a surface. When Binnig and Rohrer first produced these images, the scientific world was stunned. For the first time in history, human beings could see individual atoms, not infer their existence from indirect evidence, not calculate their positions from diffraction patterns, actually see them, mapped out as distinct bumps on a surface, each one a real atom sitting at a real location. The images were extraordinary. Gold surfaces showed neat rows of atoms arranged in the precise patterns predicted by crystallography. Silicon surfaces revealed complex reconstructions where atoms rearranged themselves at the surface into patterns different from the bulk crystal. Defects, places where an atom was missing or an extra atom sat on top, were visible as gaps or bumps in the regular array. In 1983, Binnig and Rohrer published the first atomically resolved images of a silicon surface. The image showed a 7x7 reconstruction pattern that had been predicted theoretically, but never directly observed. It was one of those rare moments in science where a theoretical prediction meets direct visual confirmation, and the match is perfect. In 1986, just 5 years after their invention, Binnig and Rohrer were awarded the Nobel Prize in Physics for the scanning tunneling microscope. The Nobel Committee recognized that their instrument had opened an entirely new window on the atomic world. It wasn't just a better microscope, it was a fundamentally new kind of tool, one that exploited quantum tunneling itself as its operating principle. Since then, the scanning tunneling microscope has become one of the most important instruments in surface science, nanotechnology, and materials research. It has been used to study superconductors, semiconductors, biological molecules, catalytic surfaces, and countless other systems. It has revealed how atoms arrange themselves on surfaces, how chemical bonds form and break, how defects in crystal structures affect material properties. But the scanning tunneling microscope doesn't just passively observe atoms, it can also manipulate them. In 1990, a team of physicists at IBM used a scanning tunneling microscope to drag individual xenon atoms across a nickel surface and arrange them to spell out the letters IBM. Each letter was built from individual atoms, positioned one at a time with the microscope's tip. It was the world's smallest logo, written in atoms, and it demonstrated that quantum tunneling could be harnessed not just for observation, but for atom-scale engineering. This capability has since been extended far beyond writing logos. Researchers have used scanning tunneling microscopes to build quantum corrals, circular arrangements of atoms that confine electrons on a surface and create standing wave patterns visible in the tunneling current. They've assembled artificial molecules atom by atom, choosing which elements go where. They've studied how single atoms and molecules behave when isolated on a surface, measuring their electronic and magnetic properties one atom at a time. All of this, every atomic resolution image, every manipulated atom, every measurement of electronic structure at the single atom scale, rests on quantum tunneling. Without the ability of electrons to cross a classically forbidden vacuum gap, none of these observations would be possible. The scanning tunneling microscope is perhaps the purest and most direct example of tunneling at work. The phenomenon that seemed to violate the rules of classical physics turned out to be the foundation for an entire technology of atomic scale exploration. And notice something important about how the scanning tunneling microscope connects back to the 4 factors we discussed and the scenario we walked through. The barrier in this case is the vacuum gap between the tip and the surface. The width of that barrier is the tip surface distance, typically a few angstroms. The height of the barrier is related to the work function of the metal, the energy an electron needs to escape the surface. The electron's energy is set by the applied voltage, and the mass of the tunneling particle is the electron's mass, which is small enough that tunneling across angstrom scale gaps occurs with measurable probability. These are the same 4 knobs, and the scanning tunneling microscope works precisely because every knob is turned to a setting where tunneling is significant. Change any of these 4 factors and the instrument's behavior changes. Increase the gap by even 1 angstrom and the current plummets. Change the surface material and the barrier height changes, altering the current at a given distance. Increase the voltage and more electrons have enough energy to tunnel at higher rates. The scanning tunneling microscope is essentially a device for controlling and measuring all 4 tunneling parameters simultaneously, turning the abstract mathematics of quantum mechanics into a practical tool for seeing the atomic world. The sensitivity of the tunneling current to distance is worth pausing on one more time, because it's remarkable. A change in the tip surface gap of roughly 1 angstrom, a distance equal to about the diameter of a single hydrogen atom, changes the tunneling current by approximately a factor of 10. This means the scanning tunneling microscope can detect height differences on a surface that are a small fraction of an angstrom, fractions of the width of a single atom. No optical microscope can come close to this. The exponential dependence of tunneling on distance, the same mathematical relationship that makes macroscopic tunneling impossible, is what makes the scanning tunneling microscope incredibly precise. There's an elegant symmetry here. The same exponential sensitivity that prevents you from walking through walls is what allows scientists to map individual atoms on a surface. The mathematics is identical. The exponential function that kills tunneling probability over large distances is the same exponential function that makes a tunneling current exquisitely responsive to tiny distance changes. The curse at one scale becomes a gift at another. The scanning tunneling microscope showed the world that quantum tunneling isn't just a theoretical prediction confined to textbooks and thought experiments. It's a real, physical process that can be controlled, measured, and exploited. It proved that the strange implications of the wave function, the idea that probability amplitudes extend into classically forbidden regions, are not abstract mathematical oddities. They are features of reality with profound practical consequences. But the scanning tunneling microscope is just one application among many. Tunneling operates across an enormous range of scales and technologies. It shapes how semiconductors work. It makes flash memory possible. It drives some of the most sensitive instruments ever built. It governs how radioactive atoms decay, and it enables the nuclear reactions inside stars. Once you understand tunneling, you start seeing it everywhere. Let's begin with one of the earliest and most elegant applications: the tunnel diode. In 1958, a Japanese physicist named Lei-O Esaki was studying the behavior of heavily doped semiconductor junctions. These are regions where two types of semiconductor material meet, one loaded with extra electrons and the other with a deficit. At the boundary between them, a thin energy barrier forms. Classical physics says electrons shouldn't be able to cross this barrier easily at low voltages. But Esaki found that at certain voltages, a significant current flowed through the junction. Electrons were tunneling across the thin barrier in enormous numbers. What made this remarkable wasn't just that tunneling was occurring. Physicists already knew that was possible. What made it remarkable was how the current behaved as the voltage changed. In a normal diode, increasing the voltage increases the current smoothly. In Esaki's tunnel diode, something strange happened. As the voltage increased from 0, the current rose rapidly, far faster than in a conventional diode. But then, at a certain voltage, the current actually decreased. It went down even though the voltage was going up. This is called negative resistance, and it's extremely unusual. In most devices, more voltage means more current, always. But in the tunnel diode, the tunneling probability changed as the voltage shifted the energy levels on either side of the junction, creating a window where increasing voltage actually reduced the number of electrons that could successfully tunnel across. This negative resistance property made tunnel diodes incredibly fast. They could switch between states in picoseconds, trillionths of a second. For decades, they were among the fastest electronic switching devices available, used in high-frequency oscillators, microwave amplifiers, and specialized circuits where speed mattered more than anything else. Esaki received the Nobel Prize in Physics in 1973 for this discovery. Modern electronics has largely moved beyond tunnel diodes for mainstream applications, but the principle behind them remains important. Every time engineers design a semiconductor device where a thin barrier separates two conducting regions, tunneling plays a role. And in some modern transistor designs, particularly as circuits have shrunk to just a few nanometers across, tunneling has become not just relevant, but dominant. This brings us to one of the most widespread applications of tunneling in the modern world: flash memory. The storage technology inside nearly every smartphone, laptop, USB drive, and solid-state hard drive on the planet. Flash memory stores data as electric charge trapped on a tiny structure called a floating gate. This floating gate is a small piece of conducting material completely surrounded by an extremely thin layer of insulating oxide, typically silicon dioxide. The oxide is only about 8 to 10 nanometers thick. The floating gate is electrically isolated. There's no wire connecting it to anything, no current path in or out. Classical physics says charge placed on this gate should stay there indefinitely because the insulating oxide barrier prevents electrons from crossing. And that's almost true. The charge does stay for years or even decades, but the charge gets onto the floating gate in the first place through quantum tunneling. When a voltage is applied to the device, it creates conditions where electrons from the semiconductor channel beneath the floating gate can tunnel through the thin oxide barrier and accumulate on the gate. Once the voltage is removed, the electrons are trapped. They can't tunnel back out easily because without the applied voltage, the energy landscape changes and the barrier becomes effectively higher and wider from the electron's perspective. To erase the data, a voltage is applied in the opposite direction. This reshapes the energy barrier so that the trapped electrons can tunnel back out of the floating gate, returning to the channel. The floating gate is emptied. The data is erased. Every time you save a file, take a photograph on your phone, or download an application, electrons are tunneling through nanometer-thin oxide barriers by the billions. Every time you delete data, they tunnel back. The entire technology rests on the ability to control quantum tunneling by manipulating voltages and barrier shapes. Without tunneling, flash memory could not exist. There would be no way to move charge onto or off of the floating gate. The next application takes us somewhere very different, into the world of superconductivity and some of the most sensitive measuring instruments humans have ever built. Josephson junctions. In 1962, a young British physicist named Brian Josephson, then still a graduate student at Cambridge, made a theoretical prediction that stunned the physics community. He predicted that if you took two pieces of superconducting material and separated them by an extremely thin barrier, just a nanometer or two of insulating material, something extraordinary would happen. Pairs of electrons in a superconductor, called Cooper pairs, could tunnel through the barrier together. This prediction had several remarkable consequences. First, a supercurrent could flow through the junction even with zero voltage applied. Electrons would tunnel continuously across the barrier, maintaining a flow of current without any driving force. Second, if you did apply a small voltage, the current would oscillate at an extremely precise frequency directly proportional to the voltage. This alternating current Josephson effect provides one of the most accurate ways to measure voltage ever discovered. Josephson's predictions were confirmed experimentally within a year. He received the Nobel Prize in Physics in 1973, sharing it with Asa Key and another physicist. He was only 33 years old. Josephson junctions are now the core component of devices called SQUIDs, which stands for superconducting quantum interference devices. A squid consists of a superconducting loop interrupted by one or two Josephson junctions. The tunneling current through the junctions is extraordinarily sensitive to magnetic fields threading the loop. Even the tiniest magnetic field changes the conditions at the junctions. altering the tunneling current in a measurable way. How sensitive are squids? They can detect magnetic fields as small as a few femtotesla. A femtotesla is 1/quadrillionth of a Tesla. Earth's magnetic field is roughly 50 microtesla. A squid can detect fields roughly 10 billion times weaker than Earth's. This sensitivity has made squids essential in neuroscience, where they're used to measure the minuscule magnetic fields produced by electrical currents in the human brain. They're used in geology to study rock magnetism. They're used in fundamental physics experiments, searching for exotic phenomena. All of this sensitivity traces back to quantum tunneling through the thin barriers in Josephson junctions. Now, let's leave engineered devices behind and look at tunneling in nature. Because long before humans built tunnel diodes or scanning tunneling microscopes, tunneling was already at work inside atoms. Radioactive alpha decay is one of the oldest known forms of radioactivity, and it's a textbook example of quantum tunneling. In alpha decay, an unstable atomic nucleus spontaneously emits an alpha particle, which consists of 2 protons and 2 neutrons bound tightly together. This is the same as a helium-4 nucleus. Here's the problem that puzzled physicists for decades before tunneling was understood. Inside a heavy nucleus like uranium, protons and neutrons are held together by the strong nuclear force. This force is extraordinarily powerful at short range, creating a deep energy well that traps the particles inside. But the strong force has a very short reach, only about a femtometer, a millionth of a nanometer. Beyond that range, the force drops off sharply. Meanwhile, protons carry positive electric charge. Inside the nucleus, the strong force overwhelms the electrical repulsion between protons. But at the edge of the nucleus, where the strong force fades, the electrical repulsion between the positively charged alpha particle and the remaining positively charged nucleus creates an energy barrier. This barrier is called the Coulomb barrier, named after the French physicist who first described the force between electric charges. The alpha particle inside the nucleus doesn't have enough energy to classically climb over this Coulomb barrier. If you calculate the energy of the alpha particle bouncing around inside the nucleus, it falls short of the barrier height. Classical physics says the alpha particle should be permanently trapped. It should never escape. And yet, uranium nuclei emit alpha particles all the time. They do it at a predictable rate. Half of a sample of uranium-238 will decay in about 4.5 billion years. The alpha particles escape despite not having enough energy to overcome the barrier. This was exactly the problem that George Gamow solved in 1928 using quantum tunneling. The alpha particle's wavefunction extends to the edge of the nucleus. Inside the nucleus, the wavefunction oscillates normally. At the Coulomb barrier, it begins to decay exponentially. But the barrier, while tall, is not infinitely wide. At sufficient distance from the nucleus, the electrical repulsion drops off and the potential energy falls below the alpha particle's energy again. If the wavefunction retains any amplitude at that distance, the alpha particle has a non-zero probability of being found outside the nucleus. Free, escaped, decayed. The tunneling probability in this case is extraordinarily small for any single attempt. The alpha particle bounces back and forth inside the nucleus billions upon billions of times every second, hitting the barrier walls at a tremendous rate. Each collision represents one attempt to tunnel. The probability of success on any single attempt is vanishingly small. But the alpha particle makes so many attempts per second that eventually on one of those attempts, tunneling succeeds. The alpha particle appears outside the nucleus and flies away as radiation. Gamov's model beautifully explained something that had been mysterious for decades. It explained why different radioactive elements decay at vastly different rates. Elements with taller or wider Coulomb barriers have lower tunneling probabilities per attempt, so their nuclei survive longer on average. Elements with thinner or shorter barriers decay faster. The half-life of a radioactive element is directly related to the tunneling probability through its nuclear barrier. Gamov could calculate approximate half-lives from the barrier shapes, and the results matched experimental observations across a range spanning more than 20 orders of magnitude, from microseconds to billions of years. It was one of the early triumphs of quantum mechanics. Now let's go even larger. Let's go to the stars. Because quantum tunneling doesn't just help nuclei fall apart, it also helps them come together. And without this, every star in the sky would be dark. Stars produce energy through nuclear fusion. Deep inside a star's core, hydrogen nuclei, which are simply single protons, collide and fuse together, eventually forming helium. This process releases an enormous amount of energy. The energy that makes the star shine. It's the energy that warms our planet. It's the energy that drives photosynthesis, weather, ocean currents, and ultimately all life on Earth. But there's a problem. For two protons to fuse, they have to get extremely close to each other, close enough for the strong nuclear force to grab hold of them and bind them together. The strong force only operates at distances of about 1 femtometer. Beyond that range, it has no effect. And protons are both positively charged. Positive charges repel each other. As two protons approach one another, the electrical repulsion between them creates a Coulomb barrier. Exactly the same type of barrier we saw in alpha decay, but now working in the opposite direction. Instead of trapping a particle inside, this barrier prevents two particles from getting close enough to fuse. The core temperature of our sun is roughly 15 million degrees Celsius. That's enormously hot by everyday standards. But when you calculate how much kinetic energy protons have at 15 million degrees, it turns out to be far less than the energy needed to classically overcome the Coulomb barrier between two protons. The classical barrier height for two protons corresponds to a temperature of roughly 10 billion degrees. That's roughly 700 times hotter than the sun's actual core temperature. A classical calculation predicts that at the sun's core temperature, essentially 0 protons should have enough energy to get close enough to fuse. The rate of fusion should be negligible. The sun should not be shining. And yet, it is. The sun has been steadily fusing hydrogen into helium for roughly 4.5 billion years. It currently converts about 600 million tons of hydrogen into helium every second. The energy released by this process is what keeps the sun hot. What creates the pressure that prevents the sun from collapsing under its own gravity, and what produces the sunlight that crosses 93 million miles of space to reach Earth. If fusion stopped, the sun would gradually begin to contract and cool. The resolution is quantum tunneling. The protons inside the sun's core don't need to classically overcome the Coulomb barrier. They tunnel through it. Let me walk you through what this looks like in practice, because the conditions inside the solar core are staggering. The core of our sun has a density of about 150 grams per cubic centimeter. That's roughly 13 times the density of lead and about 150 times the density of liquid water. In every cubic centimeter of the solar core, there are approximately 10 to the 26th protons, a number with 26 digits. These protons are moving at tremendous speeds, colliding with each other constantly. The temperature of 15 million degrees Celsius means the average proton is moving at roughly 500 kilometers per second. At any given moment, every proton in the core is being jostled and slammed by its neighbors billions of times every second. Now picture a single collision. Two protons are hurtling towards each other in this unimaginably dense, unimaginably hot environment. As they approach, their positive charges repel each other with increasing force. The Coulomb barrier grows steeper and steeper. The protons slow down. Classically, they would simply bounce off each other and fly apart, never getting close enough for the strong nuclear force to reach across and bind them. This is what happens in the overwhelming majority of collisions. Two protons approach, the electrical repulsion pushes them apart, and they fly away from each other without anything happening. No fusion, no energy release, just a bounce. But in a tiny fraction of collisions, something different occurs. As the two protons approach and their wave functions begin to overlap, there's a small probability that one proton's wave function extends through the Coulomb barrier far enough to reach the region where the strong force operates. If this happens, the strong force grabs hold. In an instant, the two protons are bound together. One of them converts into a neutron through a process involving the weak nuclear force, emitting a positron and a neutrino. The result is a deuterium nucleus, one proton and one neutron bound together. Energy is released. Fusion has occurred. The probability of this happening on any single collision is almost inconceivably small. For two protons at the sun's core temperature, the tunneling probability per encounter is roughly 1 in 10 to the 28th power. That means for every 10 billion trillion collisions, approximately 1 succeeds. If you picked any two individual protons in the solar core and asked whether their next collision would produce fusion, the honest answer is almost certainly not. The odds against it are astronomically, quite literally astronomically, large. But the sun doesn't rely on any particular collision. It relies on all of them. In every cubic centimeter of the solar core, those 10 to the 26th protons are colliding billions of times per second each. The total number of collisions happening throughout the entire core every second is a number so large that even the minuscule per collision tunneling probability produces a substantial overall fusion rate. The result is steady, reliable energy production, about 3.8 times 10 to the 26 watts every second for billions of years, all because the wave function of a proton doesn't stop where classical physics says it should. I want to be precise about something here. Up to this point, we've focused on electrons tunneling through energy barriers. Stellar fusion involves a different particle tunneling through a different type of barrier. The particles are atomic nuclei, protons, and heavier nuclei, not electrons. The barrier is the Coulomb barrier created by electrical repulsion between positive charges, not the work function barrier of a metal surface or the oxide layer in a flash memory cell. The physics of tunneling is the same. The Schrödinger equation, the exponential decay inside the forbidden region, the non-zero amplitude on the far side. But the specific particles and barriers are different. What matters is the principle. In both cases, a quantum particle encounters an energy barrier it classically cannot cross. In both cases, its wave function decays exponentially inside the barrier, but doesn't reach zero. In both cases, a non-zero amplitude on the far side creates a real probability of the particle appearing where classical physics says it cannot be. The mathematics is the same. The consequences are different because the particles and barriers are different, but the underlying quantum mechanism is identical. And the consequences for stellar fusion are extraordinary. Without tunneling, the temperature required for hydrogen fusion would be far higher than what exists inside any ordinary star. Stars like our Sun would need cores hundreds of times hotter to achieve the same fusion rates through classical collisions alone. At the temperatures that actually exist in stellar cores, tunneling is what makes fusion possible. It effectively lowers the energy threshold for fusion, allowing it to proceed at temperatures far below the classical requirement. This also explains something beautiful about how different stars behave. More massive stars have hotter, denser cores. Higher temperatures mean protons move faster on average, and faster protons approach the Coulomb barrier with more energy. The barrier is the same height, but the protons start the climb with more kinetic energy. This means the difference between the barrier height and the proton's energy is smaller. And we know from our earlier discussion that a smaller difference means gentler exponential decay inside the barrier, which means higher tunneling probability per collision. The result is that massive stars fuse hydrogen at a dramatically higher rate than smaller stars. A star 10 times the mass of our Sun doesn't burn 10 times faster. It burns roughly 10,000 times faster because the tunneling probability is exponentially sensitive to that energy difference. This is why massive stars exhaust their fuel in just a few million years, while small red dwarf stars can keep shining for trillions of years. The tunneling probability, controlled by core temperature and therefore by stellar mass, sets the pace of a star's entire life. Every star you see in the night sky, every star that has ever existed, shines because of quantum tunneling. The nuclear furnace at the heart of each one operates in a regime where classical physics says fusion should barely happen, and tunneling is what bridges the gap. Now, let's come back to Earth and talk about a less welcome consequence of tunneling. Because the same phenomenon that makes flash memory work and allows stars to shine also creates serious engineering problems as electronic circuits shrink to ever smaller sizes. Now, modern computer processors contain billions of transistors. A transistor is essentially a tiny electronic switch that can be turned on or off. In a metal oxide semiconductor transistor, the kind found in virtually every modern processor, a thin layer of insulating oxide separates a gate electrode from the conducting channel beneath it. When voltage is applied to the gate, it creates an electric field that allows current to flow through the channel. When the voltage is removed, the current stops. On and off, 1 and 0, the basis of all digital computing. For decades, engineers have been making these transistors smaller. Smaller transistors switch faster, use less power, and allow more of them to fit on a single chip. In the early 2000s, transistors had features measured in hundreds of nanometers. Today, leading-edge chips have features measured in just a few nanometers. The insulating oxide layer in these transistors can be as thin as 1 to 2 nanometers, just a handful of atoms across. And here's the problem. At these thicknesses, the oxide barrier is thin enough for quantum tunneling to become significant. Electrons can tunnel through the insulating layer even when the transistor is supposed to be switched off. The result is leakage current, a small but measurable flow of electrons that shouldn't be there. This leakage wastes power, it generates heat, and it can cause errors in computation if enough electrons tunnel through barriers that are supposed to be blocking them. This is one of the fundamental challenges of modern semiconductor engineering. The same tunneling effect that makes flash memory work by letting electrons onto the floating gate also causes unwanted leakage in transistors that are supposed to be perfectly insulating in their off state. Engineers have responded with clever solutions. They've replaced traditional silicon dioxide insulators with materials called high-K dielectrics, which provide the same insulating effect with a physically thicker barrier, reducing tunneling while maintaining the electrical properties the transistor needs. They've redesigned transistor architectures, moving from flat structures to three-dimensional designs called fin-shaped transistors that give engineers more control over the channel. But the underlying physics remains. As transistors shrink further, tunneling leakage becomes an increasingly stubborn problem. There are physical limits to how small a transistor can be made before tunneling makes it unreliable. We may be approaching those limits within the next decade or two. So tunneling is both a gift and a curse. It enables technologies that define the modern world. It powers the stars. It explains radioactive decay. It allows us to image individual atoms. But it also sets fundamental limits on how small we can make electronic circuits and how efficiently those circuits can operate. The same physics that opens doors at the nanometer scale also prevents us from shrinking technology indefinitely. This brings us finally to the answer. The answer to the question posed at the very beginning. What happens when an electron crosses a barrier it cannot pass through? The answer is this. The electron does not cross the barrier in any classical sense. It does not smash through it. It does not climb over it. It does not secretly find a hidden pathway through the material. And it does not temporarily borrow energy from the universe to boost itself over the top. None of these stories are correct. What happens is that the electron is not a classical particle. It does not have a single definite position and a single definite trajectory. It is described by a quantum state, a wave function that encodes probabilities rather than certainties. When this wave function encounters a potential energy barrier, it does not stop abruptly at the barrier's edge, the way a classical marble would stop at the base of a hill. Instead, the wave function extends into the barrier. Inside the classically forbidden region, it decays exponentially, losing amplitude with every fraction of a nanometer. But if the barrier is thin enough, a non-zero amplitude survives on the far side. Beyond the barrier, the wave function oscillates again, representing a real, measurable probability that the electron will be detected there. And when physicists actually perform the measurement, when they run the experiment over and over with identically prepared electrons, they find exactly what the mathematics predicts. Most electrons are reflected, but a small, consistent, predictable fraction appear on the far side. The fraction matches the quantum mechanical calculation with extraordinary precision. The electron doesn't break any law of physics. Energy is conserved throughout the process. Causality is preserved. The speed of light is never exceeded. Everything is consistent with the fundamental rules that govern the universe. What changes is our understanding of what a particle is and how it moves through the world. Quantum tunneling exists because quantum particles are not tiny billiard balls following definite classical paths. They are quantum entities governed by wave functions, and wave functions don't obey the same rules as marbles and tennis balls. The wave function can extend into regions that classical physics declares forbidden, and where the wave function is non-zero, there is a chance of finding the particle. That chance might be tiny. For thick barriers or heavy particles, it might be inconceivably small. But for thin barriers and light particles like electrons, it's large enough to measure, large enough to build technologies around, and large enough to power every star in the observable universe. And this is what makes quantum tunneling so quietly extraordinary. It doesn't announce itself. There is no flash of light when an electron tunnels, no sound, no visible sign that anything unusual has happened. An electron is on one side of a barrier, then it's on the other. The transition leaves no trace in the barrier itself. No hole, no mark, no pathway. There is nothing to see because there was never a journey in the classical sense. There was a wave function that extended through a region it classically shouldn't have been able to reach. There was a probability that became an outcome. But the consequences of that quiet event are everywhere. It is at work in the first stars that formed after the Big Bang, fusing hydrogen into helium through barriers that classical physics said could not be crossed. It was at work in the radioactive elements that warmed the early Earth, helping our planet retain enough internal heat for volcanic activity and plate tectonics. It is at work right now in the sun, holding it together against gravitational collapse, keeping our sky lit, sustaining every ecosystem on this planet. It is at work in the device you are using to listen to these words. Electrons tunneling through barriers and transistors billions of times every second. It shaped the history of the universe long before any living thing existed to notice it. And it will continue shaping it long after. There is something worth sitting with in all of this. The everyday world, the world of tennis balls and brick walls and marbles rolling on tables, is not the fundamental world. It's an approximation, a very good approximation, one that works flawlessly at the scales we live at. But underneath it, at the scale where matter is actually built, the rules are different. They are stranger, they are less intuitive, and they are more beautiful, because they reveal that the universe is not the rigid, deterministic clockwork machine that Newton imagined. It is something subtler, something where probability lives at the foundation of reality, where a particle's identity is encoded not in a definite position, but in a mathematical function that spreads through space, and where the boundary between possible and impossible depends not on absolute laws of reflection, but on the width and height and shape of an energy landscape and the mass of whatever is encountering it. The classical world tells you what cannot happen. The quantum world tells you what probably won't happen, and then, very rarely, lets it happen anyway. That difference, the gap between cannot and probably won't, is where tunneling lives. And in that gap, stars are born, technologies are built, atoms reveal their faces for the first time. The forbidden becomes merely unlikely, and the unlikely, repeated enough times across enough particles and enough eons, becomes inevitable. This single phenomenon, quiet and invisible, operates at the heart of atoms, inside the cores of suns, across the junctions of semiconductor devices, through the oxide layers of memory chips, and between the tip and surface of a scanning, tunneling microscope. It has been shaping the universe since long before life existed. And it all comes from one idea. A quantum particle's wave function does not stop where a classical particle would. It reaches further. it extends into the forbidden. And sometimes, on the other side of the impossible, it finds a way through.